Hello, today I'm gonna talk about the big O and how we can make a function perform better using a better algorithm. First example I have here is just to simply find the minimum number of the array that will be passed in as an argument. So I have my min that is accepting an array. So simple here. I'll first declare the minimum number. The min is the array dot first. I'll start with the first element, and I'll just simply iterate over each do L. I'll just replace min if L element is less than whatever the previous min value is. So and then later I'll simply replace the min. Okay, so I have an example over here. Obviously, this is gonna return -8 because -8 is the minimum number, obviously. So let's check if this is true. Oh, okay. Oh, I got some examples that are not commented out, so still get a -8. Let's do it again. Simply, I get -8. So to talk about the big O of this one, anything that that I'm using the iteration of an array, it's gonna be the big O of 1. I mean n is O of n. Is because I'm iterating each or the array that I'm being passed on as an argument, and I'm iterating over each time to compare if the minimum the element is smaller or greater than minimum, and then if the element is smaller than minimum number that I said, I'm just going to simply replace that. So the only iteration that is required in this one is just one time over the array. So the big O will be simply the O of n. Okay, this one is a warm-up. Here I have a second example. The largest contiguous subsum of a list array that will be passed on as an argument. So I have an example over here. I got 2, 3, -6, 7, -6, 7. So here, when I'm talking about the largest contiguous subsum, I would say like largest contiguous subarray of this list. So let's say 2 and 3, that would give me 5. 2, 3, -6 will give me -1. 2, 3, -6, 7 will give me 6, and so on and so forth. So what would be the largest contiguous subarray that will give me the largest sum? So here in this example, I have already computed in my head without typing any code. This would be 7, -6, 7, because this would yield 8, and there is nothing in this list as a subsum that's going to return a greater value than 8. In the second example, it would be 14, because 1 and 13 will give me the largest subsum of this list. And here, list number 3 is all negative numbers, so it will simply return the largest number of all of an array that is all negative numbers. So let's start with this. So I'll say the largest is gonna be the list dot first. And intuitively speaking, I would think that I would have to use the nested iteration. So I would start with 0 to list dot length, not including the list dot length, because the index starts at list dot length -1. Dot each do. I would say the first one is the start index, and then I would start at start index, iterating all the way to the list dot length, not including the length itself, do, and that'll be the end index. Okay, so I would say sum, I'll compute the sum is equal to list of start index to end index. That will give me the sub array of the array that we are looking at. Dot reduce plus sum. That will just give me the sum of the array that we are looking at, and we're going to replace the largest with that sum if the sum is greater than largest. Yep. And then I would simply return the largest here. Okay, so here we're iterating, we're using a nested iteration, which means that the big O of this function is going to be the n squared. And squared. Because here we're iterating over the start index that we're going to pivot with, and then we're iterating again from the start index to the end index. So let's try this. I'll comment these out. Yeah, I did. Okay, I got an 8, 14, and -1. Yeah, cool. But then this one is not so, I would say, efficient. I think I can do this better. Instead of iterating twice in a nested loop, I can just iterate once and find the largest subsum of this list. And the idea comes is that if you look at list number 1 and number 2, here when I'm iterating from 2 to -6, the sum is going to be 2 plus 3 plus -6 is going to be -1. So up to this point, this means that it is a net negative to have the sum of these included in the entire array. So it's okay. It is safe to assume that we're going to have to ignore -6 over here, because -6 is whenever the -6 is included, it's going to be a net negative. So it's not going to help finding the largest sum. So what we want to do is we want to keep whatever we had before we added the -6, and then we want to move on. We want to start with 7 and see if any of the subsums in the rest of the array is greater than whatever we had before we added negative sum. This one is a pretty clear example of what we are trying to do here. So if we started with -1, 1, which is the first element, and we hit 15, this is going to be the net negative of 1. So we want to keep whatever we had before we added -15, which is 14, and here it'll be 5, and the list number 1 it'll be 5, and we want to continue over to see if rest of the array returns any subsum that is greater than 5 in list number 1 or 14 in list number 2. This one obviously does return, which we have it over here, which we have 7 to -6 and 7. That's going to return 8. So we're going to replace that. We're going to replace the 5 with 8 here, but we do 7 to 7 -6 7, which is 8. Similarly, 14 is greater, so this is the reason that we want to keep the original largest that we had before adding an element that would make the largest sum net negative, because in this case whatever we had before the net negative addition was greater than whatever would be followed. So that is the idea of iterating on the list just once. So let's put that into a Ruby code. So I'll just put it underneath here. Cool. So I would say the current sum is list.first, and I would say the largest sum is going to be the current sum. Yep. So let's say the list dot each do element. Okay, so if the current sum plus the element is less than, I think I'm gonna have to say 0 over here, is less than 0, I would reset the current sum is equal to 0, and I'll move on. Else, if that's not the case, I would say the current sum is equal to current sum plus 1, which I'll just use a syntactic sugar for this, and I'll replace the largest sum is equal to current sum if the current sum is greater than the largest sum. And here one more time, and then simply I'll return the largest sum at the end. So here I'm only iterating once. I'm setting the current sum equal to 0, and then largest sum is equal to current sum, just to give a first initial declaration of the a variable. So I'm iterating over the list just once, and if the current sum plus the element that we're looking at is less than 0, I'm resetting the current sum equal to 0, but then I'm not doing anything with the largest sum because we want to keep the largest sum, previous largest sum, in order to compare with whatever will be followed after. So else, if the that means the element that we're adding is gonna be helpful, or most of the cases, unless the element is 0. So I'm just going to add current sum is equal to current sum plus element, and then I'll replace the largest sum is equal to current sum if the current sum is greater than the largest sum. And that way we can keep track of the current sum as well as the largest sum. And after the iteration, which we'll do just once, I would return the largest sum. So let's actually, here one caveat of this one is that we're going to have to do return list.min if list.all, which the element is all negative, because this would not work for any list that has all the elements that are negative. So I would add this this line over here. This would not affect anything to the big O because these are a separate it's a separate iteration or operation. This is big O of n because we're iterating this list once, and then here separately we're iterating O of n. And here, so finally we have O of 2n, but then we always obviously drop the constant, so it is big O of simply big O of n. So let's test it out. So commenting it out, cool. All right, let's. Yeah, 8, 14, and negative. Okay, I would say max over here. Obviously, I was thinking about the minimum too much, so. Yeah, cool. 8, 14, and negative 1. Yep. So there, depending on the algorithm, you can make any of the searching or whatever your algorithm is, make drastically perform better. Well, big O of n squared compared to big O of just n is a huge improvement, because the time scale that we were talking about is here is exponentially greater. It's quadratically, it gets larger and larger, but then this one it gets larger linearly. So if you look at the graph, it's just so much better in terms of the performance. Yeah, and for the next videos, I'll be talking about the big O's for a couple of times. I'll covering how we can make any function that it's going to perform better. The goal would be to make the big O of a constant, which is 1, but it's not always the case. Then it is not always the possible. So we'll try to make any algorithm that is efficient in terms of time and the space. Okay, that's it for me.